Good afternoon, everybody. Welcome to Dr. Hugh Ross's Paradox class. It's great to see everybody here live and in person, especially Nancy Martin. It's been a year. So good to see you. Nancy's been a part of this class since the last millennium, like me, I think. So it's really good to see you. Hugh is with us this morning. He's going to be doing a talk on the dates for Noah and Adam and Eve and the Tower of Babel. So that's good. This has really been fun to get what feels like some hard and fast dates on these biblical events. It's really, really been fun, Hugh. Thank you. And Hugh's going to be with us for the next 2 Sundays. On September 7th, Vance and Carol Nordman and Nancy Weigel are going to be here talking about the Jesus film. And Nancy's kind of the worldwide sponsor for the Jesus film. I asked her once how many times she's seen it, and it's been like 100 or something. She probably could quote it from memory. And then Hugh will be back for 4 consecutive Sundays. October 12th, Dr. Mark Clark is with us. Remember, he's the one that did that talk on the book on Daniel that he wrote. And then October 26th is what? What's the 26th? Skeptics Forum, right. Okay, as of right now, the Skeptics Forum is going to be in this very room at this same time on October 26th, going till 2 o'clock. And as we've mentioned before, it's kind of a reversal for what Hugh usually does. He usually gives a fairly long lecture, and then there's time for Q&A at the end. This is mostly about Q&A, and he will say something up front that's appropriately controversial, get a bunch of questions going. But this is mostly for not us. This is mostly for skeptics. So if you have people in your life that have intellectual questions about their faith or any kind of questions about their faith, and you feel like they would benefit from hearing Dr. Hugh Ross, this is the time specifically designed to invite them. So October 26th, right here, in place of Paradox class, same time. So, Sherlock Holmes and Watson are out camping. They decide they want to go camping one night. And they get their tent, and they get all their stuff, and they go out in the woods, and they pack their tent, and they tuck in for the night. And in the middle of the night, Sherlock Holmes wakes up, and he bumps Watson, and he says, "Watson, what do you see?" And Watson opens his eyes, and he says, "I see the stars." And Holmes says, "Well, what does it mean?" And, Watson's always really impressed with how Holmes can do things. So he starts to go on about how God is great and the grandeur of the stars, and we can tell the age of the universe. And Holmes says, "No, you fool. It means somebody stole our tent." Speaking of thievery, somebody here at the church stole our microphone. So we're stuck with this wired thing. So since it has a limited length, unlike the wireless one, we've got to do Q&A up here. So I'm going to put this back. Hugh's going to do his talk. When it comes time for Q&A, you need to line up over here at the microphone. And as always, Hugh will take questions on any topic. So let's say a prayer, and we'll get to Dr. Hugh Ross. Dear Heavenly Father, thank you for this class and the opportunity we have to think through these most intelligent and deep questions of our faith. We know that every question can be answered, Lord, and we just thank you for that. We thank you for that confidence. We thank you for Dr. Hugh Ross, what he has meant to me and to each one of us in this class for all these years that we've been listening to his talks and getting us excited about our faith with our mind as well as our emotions. Thank you, Lord. Bless each one of us as we listen to Dr. Ross and as we go our way this afternoon. Thank you, Lord. In Jesus' name, amen. Please welcome Dr. Hugh Ross.
Well, thank you. So I get settled here. The Skeptics Forum, October 26th. Ideally, how I want that Skeptics Forum to go is where it's all Q&A. Ross says sometimes I say a few words to get things started, so I'll come with some controversial discoveries to talk about. But literally, as soon as someone comes to the microphone, I stop talking. The rest of the time is for Q&A. This is an opportunity to invite your non-Christian friends, Christian skeptics, anyone who's got questions. We do have one rule for the Skeptics Forum. We don't want any softball questions. We want the hard questions. So invite people who've got those kinds of questions, people who've been frustrated not getting answers, bring them here. And hey, if I don't have an answer, I'm going to ask one of you here to be able to answer the question. So we'll go with that. Okay, what I'm going to talk about this morning is one of the most controversial things about the Christian faith, and that's the date for when God created Adam and Eve, the date for Noah, the date for the flood, the date for the great scattering, dispersion of humanity that you see in Genesis 10 and 11. And we're going to work backwards because the easiest date to establish is the most recent date, the date for the dispersion of humanity throughout all of Africa, Asia, Europe, and Australia. And we're going to go work back to the date for Noah. And then we're going to end with probably the key point. How do we deal with the dates that are being thrown out where people say, hey, if we look at the genetics, this means that Adam and Eve is created somewhere between 300,000 years ago and 50,000 years ago. That's really how big the error bar is. And doesn't that contradict what the Bible says? So let's jump right into it. Last Sunday, we ended with the 4 methods that people are now using to date when the great dispersions happen. And what's remarkable about the biblical claim in Genesis 10 and 11, it's God scattering humanity from one small region of the world into literally all of Africa, all of Europe, all of Asia, and all of Australia, New Guinea, and Tasmania. And what we're going to see is that we now have dating tools that for the first time are actually able to pin down when these events happen. 4 independent tools, and they're all giving the same dates, showing that these migrations happen simultaneously throughout the old world. And so the 4 methods are, number 1, for the first time, we actually have the remains of humans that date sufficiently far back in time. We can tell when the first humans, based on the remains, entered places like Borneo, the Philippines, Japan, Tasmania, as well as Western Africa, and parts of Northern Europe. And that's only been the case recently, because even if you go back a decade ago, they said, well, the earliest remains we have are basically 15,000 years ago. We now got remains that go back earlier than 40,000 years ago. And likewise, we have the artifacts that you can see associated with humans, and we're able to distinguish between the artifacts that are associated with, say, Homo erectus, the Neanderthals, the Denisovans, and modern humans. Because when humans come upon the scene, their technology rapidly advances. And so it doesn't take long for humans, for example, to be able to develop a bow and arrow. And so what we see with the hominids that preceded modern humans is that they were using tools, but they consisted of a single piece of wood or a single rock. And yes, sometimes they were able to shape the rock to make it more effective, make it a scraping tool. But what's unique to anatomically modern humans, they were able to take pieces of wood, a stone, be able to take sinews, wrap them together to make a hafted spear, be able to take, again, sinews and wood and rocks and be able to make bows and arrows. And so quickly, humans were developing fairly sophisticated tools. And what's really brand new is we now have evidence for the beginning of humans preparing food and cooking food. And as I mentioned last week, we had no choice. What's different about anatomically modern humans compared to Neanderthals and the Denisovans is that we don't have strong jaw muscles. We don't have big teeth. We don't have big jaw bones. And so in order to survive, we're forced to prepare our food and cook our food, because if we're like the Neanderthals and have to subsist on raw food, there's no way we could get the calories we need to live. But fortunately, God gave us a brain whereby we could use our brain to be able to quickly develop the methods whereby we can prepare food and cook the food so that we can actually take raw vegetables, raw meat, raw fruits, and process them in a way that with our weak jaw muscles and teeth structures, we could actually chew the food and actually gain the calories that we need. And what's also unique about anatomically modern humans, we need way more calories than, say, the Neanderthals. Now, the Neanderthals were bigger than us. They were more muscular than us. You would think that they would need more calories to survive, but we need more calories than they do, because literally a third of what you eat supports that 3-pound brain you got. And so we need to consume more calories, but we have the capacity to consume more calories because we could actually harvest vegetables that were poisonous to everybody else. But because we were grinding them and roasting them and boiling them, we were able to consume foods that were poisonous to other animals, but because of the way we prepared them, they now became a source of nutrition and rich calories. And the best example of that would be a whole class of vegetables called the vetches. They're poisonous. If you eat them raw, they will kill you. But if you gather them, grind them up, roast them, and boil them, they're now safe to eat. And so early humans were able to basically gather quickly the calories they needed. The other thing about humanity is because we're eating soft foods made soft because we're preparing them and cooking them, we could actually get the calories we need in just a few minutes. Now keep in mind, we need more calories than the Neanderthals. Modern research that I'm citing in the book that's come, by the way, the book Noah's Flood Revisited, it's now available on Amazon for pre-order. So the book is finished. You can see the book there. So you can tell your friends they can have the book delivered to them as soon as Amazon makes them available. They actually have the books in their warehouse right now. But I cite research studies there where they basically determine that the Neanderthals, the Denisovans, and Homo erectus were spending between 4.5 and 7 hours a day chewing their food. Now, how much time do you spend chewing your food on a daily basis? And keep in mind, you're needing more calories than the Neanderthals do. Well, studies show that the chewing time for humans ranges between 7 and 72 minutes. I think teenage boys fall in the category of 7 minutes. They just gobble their food right down. I remember doing a conference with college students, and I couldn't be amazed how quickly they gobbled down their food, even though they were consuming more food than I was. But those of us who are older, we kind of enjoy chewing our food, so we take longer. But the longest time is 72 minutes, and the average is 19 minutes. Now, I'm not talking about the time you spend eating your food and conversing with members of your family, just the time you spend chewing the food. Average is literally 19 minutes. Whereas for these bipedal primates that are bigger and stronger than we are, we're talking anywhere from 4.5 to 7 hours. The other thing we notice too is that because we don't use much energy to consume our food, because we're preparing our food, we can socialize while we eat. If you go to the zoo and watch the orangutans or the gorillas eat their food, what you notice is they grab their food, they go off by themselves, and they chew the food. And because they're eating their food raw, and in the zoo we tend to help them a bit. We actually skin the carrots off so it's easier for them to chew. But put them in the wild where they got to gather the food and then they got to consume it. what you notice is they go off by themselves and they literally spend hours chewing their food. We humans spend 7 to 72 minutes chewing our food, but we're doing other things. How many of you work while you take your lunch break? Okay? That's what I do. I'm working on my computer while I'm consuming my food. I'm doing research. I can go through the journals. I can do all that because of how little energy it takes to actually eat the food. But it's mainly because of the way we prepare the food in advance, we're able to get away with that. Well, again, if we were to go back 5 years ago, the earliest evidence we had for humans cooking their food was 13,000 years ago. We now have evidence that pushes that back to 40,000 years, basically making the point the very first humans were cooking their food and preparing their food. And then we got the genetic analysis. Now, the first three methods, you're basically getting direct dates because you can use carbon-14 dating. The genetic analysis is mathematical, and so I'll talk about that at the end. But here are the dates you get for Europe. Okay, if you just look at the fossils of humans that are anatomically modern, they date back between 39,000 and 45,000 years ago. The artifacts that are associated with anatomically modern humans, notice you get the same range of dates, 38 to 42,000 years ago. Earliest evidence we have for them cooking food, 40,000 years ago, and then the genetics, 39 to 45,000 years ago. So for the first time, we got 4 independent methods. They're all giving us the same dates. The other thing that really shocked the researchers who were doing these studies was we see the settlement and colonization of, say, southern Italy and Greece happening the same time as northern France and Germany and Poland. So we got the settlement of northern Europe happening the same time as southern Europe. This is evidence what we see in Genesis 10 and 11, how God is aggressively scattering humanity after the flood into the entire range of the old world. And so we see the settlement of northern Europe the same time as southern Europe. Totally unexpected. Nobody believed this until they actually had the data that said, wow, northern Germany is being settled at the same time as southern Greece. You would expect that the southern regions would be settled first, southern Greece being close to the Middle East. You expect that to be settled, Spain last of all, and then places like Germany and France and England and Scotland would be later. You'd expect people to move, but that's not what we see. We see Scotland being settled the same time as Italy and Greece. And then what we noted here are the 2 places in the Middle East where they have found early evidence for cooking, but we now have also found it in southern Greece and in northern Greece as well. These are caves where they actually see evidence that they have grains that were being collected. The grains were being ground up into a fine powder. They were being roasted and then boiled for consumption. And again, this included grains that would otherwise be poisonous if they were not prepared that way. Okay, but these are the 2 caves where they first found the evidence, but now they have found evidence that basically extends into Asia as well as Europe and Africa, showing that cooking was happening everywhere very early in the history of humanity. And then here are the migration dates you get for Western Africa, Eastern Asia, Southern Europe, Northern Europe, and what's called the Sahel. I'll show you a map of the Sahel in a moment. But what I want you to see here is that the dates are all the same. We got Western Africa being settled and colonized the same time as Eastern Asia, the same time as Southern and Northern Europe, and the same time as Tasmania, Australia, and New Guinea. Again, within the range of the errors. And again, we have the genetic dates, which are consistent with the carbon-14 dates. Now you say, well, why this spread of errors like 40 to 45,000 years ago? Well, carbon-14 dating has a limit. The half-life is 5,715 years. So when you're getting earlier than 40,000 years ago, you're getting near the limits of what you can get through carbon-14 dating, and the error bars are typically plus or minus 2 to 5,000 years. But within the error bars, notice the dates are all the same. And this has never happened before in human history, where we see the simultaneous aggressive migration of not just one region, but many regions taking place at once. Now, let me see if I can show you a map. What's interesting, you have a region called Sunda, and keep in mind we're looking at a time when sea levels are 45 meters or more below where they are today. And I think I showed you a map last week. Let me see if I can go back to this. Yes, here we go. Okay, this is showing you the sea levels that existed during the last ice age. And when you have sea levels that are 45 meters, that's 160 feet less than what they are today, that will allow you to have land bridges that join France to England, that basically connect Japan to the Asian mainland. Borneo, the Philippines are all connected. And you also have New Guinea and Australia connected and Tasmania connected. And so we see a range of dates, 19,000 to 71,000 years ago, when the sea levels are low enough that it could permit this rapid migration. You also get a few times earlier than 71,000 years ago, but the windows are quite brief. So this is basically establishing the window for the great migrations that we see stated in Genesis 10 and 11 would be occurring between 19,000 and 71,000 years ago. This is when the sea levels are low enough to permit all of Asia, all of Africa, all of Europe, including England and Scotland, and all of Australia, New Guinea, and Tasmania to be inhabited. Now, what's also interesting is that this just got published literally 3 months ago. What they have found in the Sunda region, basically the islands that are really close to Australia, the sea levels were low enough between 19,000 and 71,000 years ago that people could actually see the land from one island to the next island all the way to Australia. Today, that's not the case. If you're in Indonesia, you cannot see Australia from Indonesia. But during the last ice age, you could. And so people living there could actually see that there was land and that there was this sea that they could cross. What has been recently discovered is they found remains of long, heavy ropes. We're talking ropes about this thick, about the thickness of a baseball, long ropes, and recognize that these were ropes that were used for seafaring boats. So it's basically establishing for the first time that people living 40 to 45,000 years ago were constructing large boats, very large boats where they needed these long ropes so they could literally migrate from Indonesia into Australia. So it explains how Australia indeed was colonized 40 to 45,000 years ago, because they've actually found evidence now that the ancient peoples were building these large boats. And unlike Noah's Ark, these would be ships that were steerable. So it's a different construction challenge. Not only do you have to have a boat that can be able to carry a lot of people and animals and their supplies, it needs to go in a particular direction, which means you need to have some kind of sailing device so that the boat will actually go where you want it to go. It's going to need a rudder. Keep in mind with Noah's Ark, you didn't need a rudder, you didn't need sails, you didn't need oars. All you needed is kind of like a barge that could just float and go wherever the winds would take it to go. But if you're wanting to colonize Australia, you need to be able to get the boat to go the direction you want it to go. So what they now have discovered is evidence that indeed they were building large boats 44 to 50,000 years ago. It's published in the Journal of Archaeological Science, April 2025, and volume 62. So you want to check it out, or just put evidence of early shipbuilding capability you should be able to find it through a Google search. In fact, if you want to get your smartphone out, this is the actual research paper that documents and explains how people were getting to this region. But as you can see in this map, there was a wide land bridge connecting Australia to New Guinea, and likewise a land bridge that connected Australia to Tasmania. So they actually referred to the Australian continent as Sahul. Sahul is more than 50% bigger than Australia is today, thanks to the fact that the sea levels were so much lower. And likewise, to get from the Asian mainland to Australia, you have relatively short sea passes, sea straits you need to get across. Okay, here's the biggest challenge of all. It's quite frequently stated by skeptics, and maybe we can get some of these skeptics to come to the Skeptics Forum, that genetics makes the human origins model we see in the Bible unacceptable. In fact, I got to speak at this at a conference last year where they were just saying it's no longer tenable based on genetics to claim that all of humanity was descended from one man and one woman as recently as, say, 100,000 years ago. They're either pushing it back 1,000,000 years, or they're saying that humans were descended not from two people, but from thousands of people. However, it's all based on mathematical genetics models. So we're not talking actual genetics data that you can recover from the past. They're basically looking at the current genetic makeup of humanity and using genetic models to infer the genetics of people that lived thousands and tens of thousands of years ago. Now, there's 3 mathematical models that they're using on the genetics. And again, I want to emphasize this is the one area where you got skeptics saying, we can't trust a literal historical reading of Genesis anymore. Genetics forces us to abandon that interpretation. And the book I wrote, Rescuing Inerrancy, basically talked about how this debate has actually penetrated into conservative seminaries, where you got seminary professors now saying we no longer can interpret the early chapters of Genesis historically and literally. The challenge is based on genetics. But as I've been speaking to the theologians making the point, keep in mind this genetic challenge is mathematical based on assumptions that cannot be proven. And however, what I am going to review for you is how these genetics models are able to give us an upper limit to how far back in time the first couple from whom we're all descended come from. And it's actually able to determine, are we descended from thousands of individuals, 100 individuals, or just 2 individuals? But a word about these mathematical models. 3 different methods are used to try to determine the date back to the ancestral couple or the ancestral population. One is looking at the mutation rates. And so, our genetics changes as we're being confronted by radiation from cosmic rays, radiation from uranium and thorium and potassium in the Earth's crust. Sometimes that will cause a mutation. And so what geneticists do is they look at the genetic diversity of humanity, they estimate a mutation rate, a natural mutation rate, and then they try to determine from that how far back in time do we have to go to where we could actually have the genetics coming from one man and one woman, or does the genetics tell us we come from thousands of individuals? And so they're looking at the mutation rates. However, the limitation is this: we can determine the present mutation rate. We don't know what the mutation rates were, say, 10,000 years ago, or 30,000 years ago, or 40,000 years ago. And one of the challenges we're facing is that humans today are globally distributed, but the mutation rate, even from present-day measurements, tells us the mutation rate is different in different geographical locations. It's also different for people from different ethnic backgrounds. And so we're assuming that the present mutation rate is the same for the mutation rates through all of human history. That may not be the case. And for that reason, people have said, well, let's actually come up with another mathematical model that we can use to try to nail down what these past mutation rates were. And there's two methods that they're using. The frequency of linkage disequilibrium, I'll tell you what that means in a minute, and the frequency of incomplete linkage sorting. So a little more complex than just looking at the mutation rate. And so the thing is with, say, the linkage disequilibrium, we're looking in the genes, the chromosomes specifically, and looking, because the chromosome is basically just a long, it's a whole bunch of genes that are all linked together. But what geneticists have noticed is there's non-random association of gene variants at different positions along the chromosome. So what they're doing is they're looking, okay, what is this non-random association looking like in the current human population, and then using what they've been able to measure to determine, okay, let's just assume that's the case throughout all of human history, and let's see if we can get a date back to the first human, or we can prove that it's not just one couple, but dozens or hundreds or thousands of individuals. Now, what makes it challenging to determine what this non-random association of gene variants is all about is it could be impacted. So like the first method, you only look at mutations. But these non-random associations can be caused by multiple effects. It could be natural selection. The environment in which the human's living could have an impact on that rate. It could be mutations. It could be genetic drift, genetic recombination, or it could be based on the structure and distribution of the population and the mating habits. And this is really the big problem with a lot of these genetic mathematical models, is that we don't mate, or I should say we don't marry like other mammal species and bird species do. If you look at the way human societies are organized, and it's not quite the case today. Today, there's a lot of freedom who you get to marry. So for example, we have travel. And so you got chances of meeting people from Asia, Africa, and Europe that you could choose for a marriage mate. But go back just 200 years, that wasn't the case. The pool of people you could have as a spouse would be from a rather limited group. And keep in mind, too, with humans, there's a social structure. And so, for example, if you're from a poor family, your chances of marrying somebody from a rich family are basically zero. Again, that's all changed in today's culture, but literally just go back 100 years. There was a social stratification that limited who you could marry, and there'd be restrictions on who you could not marry. And it's more complex on certain continents than other continents. So for example, the restrictions, say 200, 300, 1,000 years ago in Western Africa were way more severe than they were in Europe. And so this complicates trying to use linkage disequilibrium to try to get a date, to try to get an ancestral population. The third method is called incomplete lineage sorting. And it's basically looking for failures. So for example, you would expect that subpopulations of humanity would inherit the most related genes. But what they notice is this isn't always the case. And so these failures can be used as a way to try to determine the flow of genetic diversity with respect to time. But likewise, this is complicated. It's not just based on mutations. It's caused by non-random mutations. Ecosystem disturbances will affect the subpopulations. In other words, this method is assuming that the subpopulations of humanity are stable. What causes them to be unstable is if you've got an ecosystem catastrophe. So for example, what happened here in North America, where you had these native humans inhabiting southwestern America. And it was great as long as you had decent rainfall and crops, but we now know, for example, that the Anasazies basically encountered a multi-decade severe drought, and they basically packed up and left. So they left their environment. So that's an example of an ecosystem disturbance that basically affects the subpopulations of humanity. And then, of course, you've got the marriage practices, who you can marry and who you can't marry. And so basically what was happening throughout a lot of humanity, particularly, say, in North America and then parts of Africa, was you can only marry someone from your tribe. Whereas in other parts of the world, you could marry outside your tribe. Again, this affects this. But the interesting thing is, I'm going to be showing you the data, is that even though you got these three methods, they're all coming up with roughly the same dates for going back to the first couple from whom we're all descended. And there's now a recognition that indeed we could be descended from one couple, based on the fact that part of this genetic study is that we all get our mitochondrial DNA from our mothers, which means you can look at the mitochondrial DNA in different individuals and realize you're only going to be getting a trace through the females. And likewise, you can look at the Y chromosomes, and only males have the Y chromosome, and so you can look at that and get a trace through the male line. So technically, you could use the genetic diversity of humanity and determine how far back you got to go to where you could say, hey, we all come from this one man, or we all come from this one woman. Now, the genetics models, because they're complex, they can't identify the woman, and so when you read the scientific literature, they talk about the mitochondrial DNA eaves, which is basically telling us there's about 8 to 10 different options as to which woman from whom we're all descended. Again, it's based on the fact there's multiple factors that determine the mathematical models here. Now, the biggest problem with this is that the field experiments, so you got these mathematical models, which are based on multiple assumptions, and incidentally, all three of these mathematical models come from a naturalistic perspective. They're assuming there's no supernatural interventions. And so it's strictly, and they're also assuming that we can explain all of life here on planet Earth from natural selection, mutations, gene exchange, and epigenetics from a single bacterium that existed 3.8 billion years ago and diversified naturalistically. So it's all built on assuming that model is correct. And from a biblical perspective, that model is not correct. From a scientific perspective, we can demonstrate, hey, if that model was correct, we would assume that the fossil evidence would be consistent with the genetic evidence, and it's not. So for example, the clocks, the genetic clocks typically give dates that are as much as 250 million years out of sync with the fossil evidence. So that right away tells us there's issues with these naturalistic assumptions. And this is now being admitted in the research journals. The big challenge, though, is that field experiments on mammals show that the genetic models only yield upper limits back to the ancestral human pair. So the dates I'm going to be showing you, keep in mind they're upper limits. They're not actual measurements of when that first human said, but they're reliable in the sense we know it can't be any earlier than these dates. Now, the field experiments on mammals are basically done to test the mathematical genetics models, and typically what they do is they'll take, say, a sheep or a goat or a horse, where they have a male and a female, where they measure the genetics of the male and the female, and they put them on some isolated island where there's no other horses or sheep that are available to mess things up, and they let them reproduce, and let them reproduce for, say, 10 or 15 generations. They come back later, they look at, say, the 1,000 sheep that have all been descended from this one male and one female sheep. They measure their genetic diversity and see how well it fits the mathematical genetics models. Okay, how do you do these experiments? Well, they said, what we need is a place where we can guarantee that there's not going to be any indigenous animals that are going to mess up the experiment. So let's see if we can find a place where there aren't any mammals, at least aren't any terrestrial mammals. And so they did find a place where they could do these experiments. It's the most isolated place in the world. If you want to get away from the human race, I know a place where you can go. It's called Kerguelen, and this is where it is, in the south part of the Indian Ocean. The nearest inhabited place is Madagascar, about 2,000 miles away. So yeah, you're literally away from everybody. And here is a blow-up of what this place looks like. It's not tiny. It's 93 miles east to west and 75 miles north to south. So it's a fairly large island, and it's at 49 degrees south, so it's like, okay, it's not like Antarctica where it's going to be so cold that no animals can survive there. The average temperature throughout the year is running around 50 degrees, and you can survive at 50 degrees Fahrenheit. That's not bad. In fact, the coldest it ever gets is about 15 degrees Fahrenheit. The hottest it ever gets, it gets into the upper 70s. The highest temperature they got was 80 degrees. So, I mean, you can survive there. It is kind of windy, however. It's one of the windiest places in the world. In fact, some think it's the windiest place, period. They often have sustained winds that are over 100 miles an hour, and it gets up to 180 miles per hour. We're not talking a hurricane, we're just talking regular winds. So this, by the way, is the largest city in Kerguelen. It's the Port-au-Français, and has a population of 45. That's the winter population. The summer population gets up to 100. And by the way, that's the total human population of this enormous island. It basically just has one village. And this is what it looks like. You've got a few huts, you've got dormitories. It has a church, by the way. It's also got a very tiny hospital. So, and there's a barge that comes in once a year to drop off supplies for the people who live there. It says, who lives there? It's 100% scientists and a few supporting engineers. And they're doing experiments there. And you say, well, is there stuff that grows there? No trees, but there are grasses. And if you like cabbage, you'll love this place. Kerguelen cabbage. It's a unique species of cabbage, but it does grow all over the islands. But it is a fairly bleak place. So this is what most of the island looks like. No trees, and if you look close to the ground, you'll see little short grasses here. But it is a place where you could have goats and horses running around foraging for food. Okay, back to this map here. What they did, I see I'm running out of time, so I'll save this for next week. The arrow you see going up and down, that shows you where Port-au-Français is, the only village that exists on all these islands. And by the way, there was a time when they had some other people there. Basically, people discovered seals, and especially sea elephants, like to rest on this island. So there was a time in the last century, early part of the last century, where people would go there to harvest these sea elephants and get their oil and use them for lamps. This is before electricity. But they almost wiped out all the seals and the sea elephants that were there, and so they put a ban on it. The seals are beginning to come back, but really no mammals there, although they did introduce some rabbits, so there's some rabbits running around on the islands. But the second arrow you see that kind of goes off at a slant, that shows a small island called Île Haute. And it's got some wind protection because it's basically surrounded by land masses. So they chose this island to do experiments. And it's on this island where they basically took this mouflon sheep. Here's a photo of what it looks like. And there it is, wandering around. You can see there's little bits of cabbage that it can munch there on the ground, and little bits of grasses it can eat. So they took a male mouflon sheep, a female mouflon sheep, very carefully measured its DNA, left it alone on the island. And you notice the island isn't that big and is well protected from the winds, and basically just let them reproduce. And then came back decades later and looked at their DNA. Okay, we'll look at that next week. We're also going to look at what they did with these horses and orangutans. They've now done it with 8 different species. And it's really interesting, the result that they came up with, which has an enormous impact on the dates you come up with from Adam and Eve, and whether we can actually defend what the Bible declares, that all of humanity is descended from one man and one woman that God specially created relatively recently in the history of the earth. Next week, we'll cover that. Okay, we'll take questions. As always, we'll take questions on any subject, any question you can ask. I mean, I once said that in front of an audience in Oklahoma, and the first person that came up said, okay, I got a question for you. How much do you weigh? I actually answered the question. So literally, I will take any question. So, and then we're going to alternate from people that are here in the class and people that are participating online. Because we're tethered to a cable, if you want to ask a question here in Pritchard Hall, you got to walk up to the microphone here. And I love this, because now you're going to be close enough to me, I can probably hear your question. So.
Are we on? Okay. Come back here if you have questions, and we have online questions also, so we'll alternate. Doug, do you want to come on? Move. Try not to touch the mic. It's very touchy.
Okay.
Someone took our good mic, so this is all we have.
I have a mic I could do it.
Yeah, and get as close to the mic as you can. Thank you. Okay, Doug.
But I can't touch it.
Very good.
I'm sorry, I can't stand up very long. I've been rereading your book, Why the Universe is the Way It Is, listening to it as an audiobook. And I was listening yesterday to the chapter about dark matter stabilizing the Milky Way from the outside.
Yes.
And you talked about exquisite dark matter and dark matter. So what is the difference? How did the dark matter get there, and how does it point towards design, please?
Okay. Yeah. What I did in Why the Universe is the Way It Is, talk about the difference between ordinary dark matter and exotic dark matter. And what's complicated today is astronomers have stopped using the term exotic. So when they talk about dark matter, they mean the matter that doesn't interact with light. And that's the difference. Ordinary matter strongly interacts with photons. And what I mean by ordinary matter is matter composed of protons, neutrons, and electrons. And those 3 particles all strongly interact with photons, which means they're very easy to detect. Exotic dark matter, or what's simply referred to as dark matter today, is matter that does not interact at all with light or interacts at an extremely weak level. An example of that would be neutrinos.
Are there 2 types of dark matter?
Yes, 2 types of dark matter, because most of the ordinary matter in the universe is matter that's made up of particles and dust, and you don't really get to see light from ordinary matter unless you get a huge conglomeration. So you get enough protons and neutrons jammed close together, guess what? It becomes a star. And with that, you get nuclear fusion going on, and you get to see the light. But if it's just random neutrons running around in interstellar space, it's really not going to emit light. You say, how can we tell it's there? We can tell it's there because of its gravitational influence. And so we use gravity as a way to determine the amount. But it's such that the vast majority of ordinary matter is dark. It's not emitting light. And so, for example, what I do mention why the universe is the way it is that the ordinary matter that's emitting light makes up only 0.25% of all the stuff of the universe. 99.75% is made up of stuff that doesn't emit light. Now, we also know that the ratio of the exotic dark matter to ordinary matter is almost 6-to-1. There's almost 6 times as much exotic dark matter as there is ordinary dark matter. And again, I mentioned one known example is neutrinos. So for example, every second there's trillions of neutrinos that go through your thumbnail. But because neutrinos don't interact with light, they just zip through your thumb and you never notice it. Now neutrinos weakly interact with light, which means very rarely you'll get a neutrino that actually interacts, which means you can detect it. But they're very difficult to detect. So for example, what they do is they build these huge underground containers. Probably the best example of the neutrino detector, that's the one that's under a mountain in Italy, where they got literally 5,000 feet of rock above the detector, which blocks out all the cosmic rays, because the cosmic rays will give you a false signal. So you want to eliminate the cosmic rays and just get the neutrinos. By the way, most of the neutrinos hitting the Earth go right through the Earth and don't interact. But every once in a while one does, and that's how we detect it. But astronomers also believe that there are particles that don't interact with light at all, which means it's going to be, you're not going to be able to detect it except by its gravitational influence. Now, I think you're referring to is my statement in the book how it's the exotic dark matter that stabilizes the spiral structure of our Milky Way galaxy. Our Milky Way galaxy is unique in that it's got these big spiral arms that are well separated from one another. They're very symmetrical, highly stable, with very few feathers and spurs between them. And one reason for that stability is that, number one, our Milky Way galaxy has not absorbed a large dwarf galaxy in the last 11 billion years. So we've had no disturbance event in the last 11 billion years. And number two, our Milky Way galaxy is surrounded by a gigantic halo of exotic dark matter. You say, how big is it? Well, it stretches from here to halfway to the Andromeda galaxy. So if you look at the stars in our Milky Way galaxy, they form a disk that's about 100,000 light years across. The dark matter halo is 1.9 million light years across. And it's not disc-shaped, it's kind of an oblate spheroid. 90% of the mass of our Milky Way galaxy is made up of this exotic dark matter. Now you say, is that atypical? Yes, it is, by a wide margin. Typically, you have galaxies where, maybe a little more than half the mass is exotic dark matter, or even less than half the mass, but with our Milky Way galaxy, it's 90%. We don't know of any other galaxy, spiral galaxy, that has such a gigantic ratio of dark matter to ordinary matter. And for that reason, it explains why we have this remarkable stability and why we can't find a galaxy far, far away that has the conditions which would allow advanced light to be possible. So, yeah.
Do we know how it got there?
Do we know how it got there?
Yeah, the halo.
We have some ideas. So, for example, and where you get a lot more detail on this, and it looks like you want to dive deeper into this, get the book I wrote, Design to the Core, which basically goes into the latest discoveries on dark matter and what's going on with our Milky Way galaxy. So what we have, because of that enormous ratio of exotic dark matter to ordinary dark matter, the early universe forms this, what's called the cosmic web, which basically looks like a lot of soap bubbles. And what's going on with the soap bubbles is that you have the ordinary matter on the surface of the bubble, and the exotic matter is more in the core of the bubble. And that actually permits the galaxies to be far enough away from one another that it's possible to have life existing in the galaxies. So one of the early chapters of Design to the Core is all about the cosmic web, the latest discoveries in the cosmic web. But each bubble is a little bit different than the other bubbles. We happen to live in a bubble of the cosmic web, which explains how it is that our Milky Way galaxy got such an enormous amount of this exotic dark matter, and explains why the grouping of galaxies that we're in is unique. I mean, typically galaxy groups form along a filament of the cosmic web. Our local group of galaxies is formed at the nexus of 3 subfilaments, and we don't know of any other grouping of galaxies where that is the case. It explains why the local group has no giant galaxies, and where the has only 2 large galaxies that are far apart, where the dark matter halos don't overlap. And so the Andromeda galaxy has a dark matter halo, our Milky Way galaxy is a dark matter halo, but the 2 galaxies are far enough apart that the halos don't interact with one another. And that's important in order to have advanced life. So, but hey, more details in Design to the Core. Okay, got a question from the web?
We do. From Jan Pekoski. Young Earth creationists have an argument about fossilized tree trunks crossing multiple strata. What is your comeback?
Yeah, that's the polystrate fossils that they're talking about, and how you will see, say, a fossilized tree trunk with several layers around it, and they're saying that proves all the layers have to be laid down at the same time. You can go online, in fact, just Google it, polystrate fossils, and you'll see a number of articles explaining, well, there's one way it can happen, but there's other ways it can happen where you get the layers coming in sequentially. Moreover, there's cases where the tree trunk or the blade of grass can be thrust through layers that have been laid down over a period of time suddenly. A good example of that is, we don't get tornadoes here in Southern California. For those of you who lived in Tornado Alley, frequently what you'll see is a drinking straw that goes right through the trunk of a tree, and the drinking straw is intact. You say, how can a paper drinking straw be thrust through a tree where it penetrates, say, 50 annual layers? Because that may be the problem. It's similar to the polystrate thing, where you have all these different annual layers, but you actually see something penetrating all the layers. Well, if you got wind velocities of 350 miles per hour, that straw can literally be forced through all those tree trunks intact. So that's another way you can get the explanation of polystrate fossils from an old Earth perspective, but there's actually multiple ways you can make it work. You don't necessarily, you can have the tree being fossilized, all the different layers are forming at different times. But hey, just Google it, and you'll see lots of articles showing that the young Earth argument is based on assuming there's only one way it can form. There's multiple ways. Okay, Tim.
Yeah, hi, Hughes. In your book, Weathering Climate Change, you talked about a number of big sources of electricity that are being used, or energy in general, and some upcoming, like the creation of cryptocurrency that seem to be somewhat wasteful of electricity. And I'm wondering, since that time, we've had a huge increase in the demand for electricity from AI data centers. And I just wonder if you have comments about how that compares with some of the things you're talking in your book.
Yes, well, thank you, Tim. And just so you all know, I've now written a supplement sequel to the book Weathering Climate Change. It's about 30,000 words long, because I realize a lot's been published in the scientific literature and by the way, when I came with the book Weathering Climate Change, there wasn't room for me to talk about thorium, nuclear, and electricity generation, or other ways of generating electricity. This supplement that I've just finished goes into all that. So an update will be coming out soon. We're basically running out of the first edition of the book. Our plan is to release the book as is, but have with it this big edition, which covers this stuff. And so, yeah, you mentioned cryptocurrency is very electricity hungry. Likewise, artificial intelligence is electricity hungry. So what was in the first edition of Weathering Climate Change was the assumption that the demand for electricity would continue at the same rate that it has been continuing through the early part of the 20th century, What you're raising is that assumption is probably not correct. The demand for electricity is probably going to go up exponentially, which means we're going to need electricity producing sources that are going to be able to accommodate that exponential demand for electricity. And we all, so what I have in the new edition is how we can get huge amounts of electricity without burning fossil fuels and actually get that electricity for a cheaper price than we can get from burning fossil fuels. But I'm also arguing natural gas is probably going to need to be a stopgap measure, just like I said in the first edition of Weathering Climate Change. And fortunately, there seems to be some movement in that direction. It's true fossil fuels release greenhouse gases, but if you burn natural gas instead of coal, the release of greenhouse gases drops by almost a factor of 2. And that's because natural gas is CH4. When you burn it, you get water plus carbon dioxide. When you burn coal, it's all carbon dioxide. And you say, well, isn't water a greenhouse gas? Yes, it is, but if you pump a lot of water in the atmosphere, a lot of that water falls to the ground as rain. And so typically, you can put a lot of water in the atmosphere and not have it enhance the greenhouse effect, because unlike carbon dioxide, it's not stable in the atmosphere. Put more in it, more of it falls to the ground. And hey, that might actually help parts of the world that are suffering from a water shortage. So natural gas, in that sense, could be a good step. And what's also new in the scientific literature is a recognition that a big problem with coal is not just the carbon dioxide. The bigger problem is you're releasing black carbon soot. And so, for example, people have been wondering why is northern Canada and Alaska and Siberia warming at a rate far faster than we would expect from the increase in carbon dioxide. It's because the coal that's being burnt in India and China and Indonesia, the winds carry that black carbon soot and dump it on Siberia, Canada, and Alaska. And it's being dumped on what? Snow and ice. What happens when you put black stuff on snow and ice? It melts the snow and ice, and when you melt the snow and ice, you have ground that reflects sunlight, with, say, 20% efficiency, whereas the stuff that's covered with ice reflects it with 60% efficiency, which means that the ground in Canada, for example, is absorbing a lot more solar heat because you're melting the snow and ice. And literally glaciers all over the world are being melted. Don't blame carbon dioxide. The bigger factor is the black carbon soot. So what I also have new in the supplement is the health crisis in Southeast Asia due to black carbon soot. So for example, the life expectancy of people living in India, which now ranks as the most populous nation in the world, it has decreased by an average of 5 years for all of India. For the Ganges Valley, where half the population of India lives, it's decreased by 8 years. If you happen to live in the capital city, your lifespan is shortened by 12 years, strictly as a result of the black carbon soot that's being released from the burning of coal. And this is a huge financial drain on the economy of India. And by the way, for all of Asia, the entire Asian continent, the life expectancy is shortened by 3 years. So Eastern China, 5 years. And so there's now a strong motivation economically, just because of the health costs, to stop burning coal and burn natural gas instead. And I got a little thing in the supplement saying, the last administration shut down the construction of natural gas exporting ports. The new administration is saying, we think that's a bad idea. We need to build more of these ports so that we can export, because North America is sitting on huge quantities of natural gas. We can literally ship that to Asia and India, and they would actually have a source of fuel that's cheaper than coal, that wouldn't have all this particulate pollution, and the greenhouse gases would be dropped by a factor of 2. But I'm also arguing that would buy us the time to scale up thorium nuclear reactors, which I argue is the cheapest source of electricity, even cheaper than water power. And so if we can scale that up, we're going to have the electricity we need to support artificial intelligence. So, by the way, I just read a paper yesterday where it said because of artificial intelligence, half of white-collar jobs in the United States could disappear. That sounds like a huge unemployment catastrophe. Well, I'm old enough to remember when people were frightened by the fact that, hey, now that we got automatic elevators, we're going to have all these elevator workers out of work. What happened to those elevator workers? They wound up getting jobs that were more meaningful and more productive. And so, as we advance technology, it always enhances the economy. It doesn't cripple the economy. But the challenge of artificial intelligence, we're going to be taking people out of work and putting them into new, more productive jobs, but it's going to need a lot of retraining, and they're going to have to retrain fast. That's the big challenge. I mean, when we drove all the elevator operators out of employment, it was relatively straightforward to say, okay, we can train you in a month to take this job, and it's going to pay more, you're going to be more productive, you're going to be more fulfilled. They were excited. Artificial intelligence means it could be a steep learning curve to get a job that's more productive. So somebody's got to manage all these artificial intelligence systems, but that now requires that we probably have to get a lot more education, get taught more, but hey, it will boost the economy. Can you imagine what will happen when we can take the 10 million truck drivers in the United States and have them doing something else? I mean, that could literally happen within a decade, where all the semi-trucks in America are being driven by artificial intelligence. However, the big challenge with artificial intelligence today is that if you got one of these driverless cars, they're not too good at determining whether a paper bag on the highway is empty or filled with bricks that you want to avoid. A human knows the difference. Artificial intelligence does not yet know that, which is why when you do drive a driverless car, they've got 2 cameras that watch your eyes. If you're not watching the road and the steering wheel, it turns the engine off. But a time will come when they won't have to worry about that, because it'll know the difference between a paper bag with bricks in it and a paper bag that's empty. That will happen. And hey, if you go to San Francisco, you can get an Uber where there's no driver in the car. However, that car will not allow you, the artificial intelligence will not allow you to use that car to go outside of San Francisco. You can only go within, because the artificial intelligence has got San Francisco figured out, but it doesn't have the suburbs figured out yet. And so, but it's quite clear that a time will come. But it's going to, hey, I know you're into astronomy. We could be at risk. To make all this stuff work, they need to put up a whole bunch of GPS satellites that'll be able to figure out where your car is, where your cell phone is, to within 1 centimeter. We can nail things down to 1 centimeter. Artificial intelligence is going to be able to know when you're pulling the cell phone out and using it to do things you shouldn't be doing, as opposed to paying attention to what's going on in your car. So also means big government could actually be watching you in quite a bit of detail. But boy, it's sure going to ruin astronomy. We put all those satellites up. So yes. So
What's kind of the minimum we could get thorium electricity?
okay, here's the question. What's the minimum time to scale up thorium nuclear power reactors to supply all the electricity we need? A minimum of 10 years. Okay, we know thorium nuclear reactors work. We know they deliver 300 times the energy of uranium, and we know that they're safe. You can't have a meltdown. Now, I made the comment before, you can't use thorium nuclear reactors to make a nuclear weapon. You actually can, but the difficulty is it kills everybody that's involved in the manufacture. So it's a significant deterrent for using a thorium nuclear reactor to make a nuclear weapon. All the people involved wind up dying as a result. So, but yeah, what we don't know yet, because There were thorium nuclear reactors producing electricity back in early 1960s. 61 was the first one up and running. Oak Ridge still has a thorium nuclear reactor that's operational. What we don't know is what size the reactor gives the most bang for the buck. So we're going to need some time to figure out, are we better off with a whole bunch of small ones, or are we better off with a few really big ones, or something in between, or do we need them all the way across? So, but the engineering difficulties have already been solved. We just now need to work out the economic challenges. But potentially, I think we could get electricity from thorium nuclear reactors that would be half the price of water power. So, and you want to know how cheap that is? I have a friend in Canada who gets his electricity from water power, and he's got a couple of these electric vehicles, and he says, the cost of driving my two vehicles is 50 cents a month. So I think probably most of you are paying more than that for your monthly gas bill when you go to the pump. So if we can drop that down to 50 cents, wouldn't that be a great benefit?
We have some Skeptics Forum flyers, first version, so they're on the table here. Come and pick one up at the end of the class, or a couple, if you can post them somewhere. Eventually we're going to want to put them on college and maybe some high school campuses and other businesses. So here's, I don't know if you can see it from there, but there's one. Tony Barragon, sitting right back there, has been helping with this. And so we'll probably come up with some other versions too. We have at least 4 versions now. Question for you, Hugh. What is the significance of Saul's name changing to Paul? Surely more than just S and P. Do the names themselves have deeper meaning?
Okay, question was, we have the Apostle Paul in the Old Testament, or pardon me, the New Testament. His name was Saul, his name got changed to Paul. What's going on there? I could say I simply don't know, but notice that he's not the only apostle that his name changed. Peter, he was called Simon, his name got changed to Peter. And Peter means the rock. And Saul had his name changed to Paul. Commentaries I've read on this said, we don't know what's basically the significance of the meaning of the word Saul and the meaning of the word Paul, but the fact that his name was changed basically makes the point he had a dramatic conversion. And the case of Simon, Simon was kind of wishy-washy, but when he became, Peter, that's when he became the solid rock. So it's making a theological statement there, and it's hard to find a more dramatic conversion than that of Saul to Paul. He went from being a persecutor of the church, trying to wipe out Christianity, literally by imprisoning and killing all Christians, to being the apostle that took the message of Christianity from the Jews out to the entire Gentile world. And hey, he's the author of 13 books in the Bible. So commentaries I've read, it just said they think that's the key point. It's making the point that, hey, this man dramatically changed.
Thank you. Anybody else in the class? No? Come on up. We got about 5 more minutes, so.
Thank you. A question that occurred to me when you were talking about the, genetic method for estimating, the age of ancient modern humans, and I was wondering, is there, depending on how complete that genetic data is there a way to see how that genetic data from ancient modern humans may differ from our DNA today? And would that also suggest anything about the lifespan of those humans? Taking into account that we have tremendous ages mentioned in the Old Testament, Methuselah being the prime example of that. So anything that might suggest genetically how that might be possible?
Yeah, okay, so the question about do we have the remains of people that predate the flood of Noah? The answer is no, we don't. So we don't have any of those remains. And keep in mind, we're digging back into the last ice age. And so the fact that we have any human remains at all from the last ice age is quite remarkable. Because the thing about the previous ice age, it was the most dramatic ice age in the ice age cycle. I think I mentioned last week, the last ice age was a region, a time when you had these massive freezing events and melt events. So people often think of the previous ice age as one where you had ice permanently covering, say, half of North America with thousands of feet of ice. We now know the true picture is North America was covered with thousands of feet of ice. The ice would melt, the ice would refreeze, the ice would melt, and this happened dozens of times during the last ice age. Well, you can imagine if we got thousands of feet of ice melting and reforming multiple times over a period of, say, 50,000 years, that's going to make it very difficult to have any kind of this data remaining. I mean, if you've got human remains, it's going to be all chewed up multiple times as a result. And so we're looking at a handful of human remains that date back earlier than 25,000 years ago. So that makes it challenging to say, well, wouldn't it be just straightforward? We got, say, 100,000 human skeletons that date between 60,000 years ago and 5,000 years ago. We could actually recover that DNA and actually measure what the mutation rates were at different times. The problem is we don't have enough DNA evidence for that to be doable. You're literally talking, when you get earlier than 25,000 years, you can count the number of specimens on one hand. And in no case do we have a complete skeleton. You're basically looking at a fingertip or maybe a jawbone. So you've got a partial thing. And so that's what makes the genetics so difficult. You're forced to use mathematical models because we don't have the actual genetic data. And so the models I talked about are the best models that we have. There's more than those 3 models, but I chose the 3 models that have the lowest statistical errors. And next week I'll make the point. When you read the scientific literature, they only give you the statistical errors. On top of that, you've got to add the systematic errors, and they're enormous, which is why I make the point. What you got in the published literature are upper limits. They're not actual dates. We'll discuss that next week.
Okay.
Can you answer a question in 3 minutes?
Yes, I can ask one in 3
Okay.
minutes. As
Last
long as it's not
question.
as complex as Tim's.
Okay, Tim. Omnipo B has a question. The book of Enoch states that demons and unclean spirits are disembodied earthbound Nephilim and are not the same as fallen angels. Is there any truth in this?
Yeah, there are 3 books of Enoch, and one is cited most frequently as being one that should be included in the canon. Notice this, even the Roman Catholic Church does not include any of the books of Enoch in the canon. They do include 1st and 2nd Maccabees, and they include 5 other books as ones that do have wisdom that might be worth paying attention to, but they don't include the books of Enoch. Again, you can Google the books of Enoch, so even secular websites will make the point. There's sound reasons why none of these books are considered to be reliable. They're late written, so Enoch did not write these books. They put his name on it, and it's filled with speculations that we know for a fact can't be true. But it does explain why, when you talk about the Nephilim, there's 3 different models for the Nephilim that you'll see in the theological literature. One is that fallen angels impregnated human women and gave rise to the Nephilim. Another one is that demon-possessed men impregnated these women and gave rise to the Nephilim. The third one is that God prohibited the sons of Seth from marrying the daughters of Cain. But some sons of Seth violated that command and gave rise to the Nephilim. You want to know why that particular model is as popular as it is? You can blame the book of Enoch. But it doesn't explain, for example, why it is the Nephilim have supernatural characteristics. By the way, if you're interested, there's a TV series you can now watch, I think, on Netflix called The House of David, which actually does a very good portrayal of the battle between David and Goliath. But the thing we notice about Goliath, according to 1 Samuel, is that even with a short cubit, he was 9 feet 9 inches tall. He could have been as much as 12 feet tall. And it also says that he carried into battle 250 pounds of weapons and armor. And if he was strictly human, there's no way he could have done that. The problem with us being bipedal, without anything supernatural being involved, is the weight of your bones goes up geometrically, that is with the square of your height. So if you see guys wandering around that are 7 feet tall, they have a very heavy skeleton compared to someone who's 5 feet tall. Literally, the bone mass weight goes up by a factor of 4 between a little less than 5 feet and 7 feet, which explains why the taller a person is, the less mobile they are. And so it explains why these guys that are 5 feet tall playing in the NBA, they can scoot around the guys that are 7 feet tall because they don't have that huge amount of bone mass. The bottom line is there's no way a human could be mobile, a pure human could be mobile at 9 feet or greater. The tallest human that ever lived was 8'11". It was a human being that didn't stop growing. Typically you stop growing when you get into your late teens. This individual had a genetic defect where he just kept growing. But as he got up to close to 8 feet, he was exhausted all the time, and he literally died a death of physical exhaustion. And he only lived to be 39 years of age. And once he got above 7 feet, in fact, there's a Christian actor that you may have heard of. He played the role of Jaws in one of those 007 movies. He's 7'7". He's a Christian, but he's now in a wheelchair. He just isn't able to support that height. And he got confined to a wheelchair literally in his 30s. So again, no credibility to the Book of Enoch.
In prayer, if you would.
Okay. Father in heaven, we thank you for an opportunity to be alive in the 21st century when questions that people ask about the Bible and how we can test it can actually be put to the test and show that indeed your word is inspired and inerrant, the only book given to humanity that has that claim. And so, Father, I pray that this would enable us to encourage our friends, our relatives, associates, to spend significant time studying the Bible as a way to live our lives, as a way to develop a relationship with you and with all those who give their lives to you. In Jesus' name, amen. Thank you. Thank you.